Good morning, everyone. I'm going to present temporal reasoning on large-scale graphs. My name is Hassan Nazir Chaudhary, and this work is done jointly with Pietro, Alessandro, and Matteo Rossi. So initially, I'm going to motivate the problem, and then I'm going to present the proposed algorithm and architecture. So large-scale graphs represents interconnected system and events. They are found in several areas, for example, social medias such as Facebook, Twitter, LinkedIn, and so on. They are found in Internet of Things, e-commerce, video portals, and you name it. So there are a large number of areas in which large-scale graphs are found. We apply different algorithms to find the inside information in these large-scale graphs. The typical example can be page rank, community detection, triangle counting, collaborative filtering, and so on. Currently, we have large number of frameworks which provide this graph computation, and they perform distributed computation and distributed algorithms to actually find and perform these computations. However, they mostly work with static graphs. Modern day graphs are dynamic in nature, and they evolve with time. So they receive continuous updates in the graph structure. One of the very important and interesting problem would be to do pattern detection and event recognition in these large-scale graphs. However, till date, traditional graph processing systems only support the iterative graph computation, and they do not support these event detection and complex event recognition in dynamic graphs. One of the well-known area for complex event recognition and pattern detection would be stream processing. So stream processing is a very well-known area where the inflowing data into the system is treated as stream, and then different patterns are applied on this stream to find different events in this entire pipeline. However, this stream processing cannot be applied to large-scale graph since the operators in these stream processors can support a limited amount of state, and also they do not support the large-scale graph processing paradigm, which is mostly iterative in nature. So in short, currently the stream processing as well as the graph processing systems do not support event detection and pattern detection in large-scale graphs. The aim of this work is to actually work on graph processing systems and to present a system which could perform graph processing as well as complex event recognition. So hopefully till now I have motivated the problem, and this slide sort of summarizes all of the problem together. So you could see on this slide that we have a large-scale graph, and this large-scale graph receives continuous updates in its structure. So as we receive these updates, the graph dynamically updates itself. So what we want to do here is we want to install patterns on top of graphs, which provides temporal reasoning, and we would find some patterns from these graph updates. So we have a classical graph computation as well as event detection and pattern recognition, just like stream processing. So till this point, I have motivated the work, and now I'm going to present you a very high-level overview of this design. So let's talk about the proposed architecture. So since the time is very short, I'm not going to present the flow graph semantics or syntax itself, but a very high-level overview of the language model. So first we perform a graph computation. So this graph computation could be collaborative filtering or triangle counting and so on. After performing the graph computation, we could extract meaningful and relevant information in a form of subgraph, vertices, or edges. Now this meaningful information could be extracted via filtering or grouping the data by some key. Once done, we perform a temporal pattern evaluation by applying certain predicates on the data. So this is sort of a very high level overview of the language model, and we provide syntax and semantics to handle this type of formalization. So we also support temporal logic in two major ways. One of it is talking about event that happened t time units before. So we support events which happened some time units before. We also support events which occur at regular time interval by every primitive. In this case, the event would be occurring every t time units within a certain window of time. So from these two primitives, we could support temporal logic. The first one, as I said before, is ago, which represents an event which happened t time units before, while on the other hand, every support events which occurs at a regular time interval. So this slide sort of represents a flow graph architecture at a very high level. It consists of two major pieces. The first piece is master, whose job is to orchestrate the operation overall. The other part are workers, which are shown as node here, which contain the actual graph. So the job of the master is to partition the graph, to maintain the load balancing, to make it fault tolerant, and to provide coordination among different workers. In practice, master would not have any graph by itself, but its job is only to coordinate and orchestrate the operation. The other piece of this architecture are workers, which are shown as different nodes here. Each worker will have a certain partition of the graph, and then it would also have different patterns and temporal reasoning to perform on this certain graph. So you could see that this overall architecture supports graph processing as well as pattern detection over a distributed system. So that sort of concludes my presentation. This is an ongoing PhD work, and we have made this framework flow graph and tested it in many ways. In future, we are looking to extend the framework with additional simulations, and we are also providing a query optimization for our framework to have an efficient processing of queries in our system. These are two references of the presentation, and I welcome you about any questions and doubts if you have about this presentation. Thank you so very much for being patient.